All right, can you see my screen?
I can see it.
Can you see it's the Sled Wars screen?
Yeah.
Okay. All right, so I'm gonna start with that again. So we left off at the end of page 2. So question number 3, the very, very bottom. So how does increasing the starting height affect the speed? So as we increase the height, what happened to the speed? Did it increase, decrease, or stay the same?
Increase.
Increase, good. So it made it faster or it increased. Let me just log in again to Gizmos. All right, so we are on activity B. So we're going to reset the slot, scroll that up. All right, so it's reset. One sled, drag him up to a height of 25, which is there, and 100 kilograms, so that's there. And then, so we've been talking about kinetic energy and potential energy. We know kinetic is energy of motion, potential energy is stored energy. So right now, while he's at the top of the hill, he has potential energy, and then as he starts moving, it converts from kinetic to, from potential to kinetic. So what we're going to do is we need to turn on the show energy, which is up at the top. And you can see right now he has potential energy, but he has 0 kinetic energy. So then as we play, so we just kind of have to stop it as he's going, but the very top we're going to record, so in that table on the 3rd page, it says potential energy, top 25 meters, we're going to rate 24,500 joules under potential energy. At the top he has 0 joules of kinetic energy, and the total energy, you're just adding it together, would be 24,500 joules. Okay, I'm going to do my best to get to the middle. Yeah, that was not even close. All right, that's close enough. All right, so middle, it's not exactly the middle, but we're going to write 16.8 meters. And at the top, potential energy is 16,491 joules. And the kinetic energy is 8,009 joules. And they're not exactly equal because we're not really in the middle. But if you add it together, we're at 24,500 joules. Anybody need me to repeat any of those? Oh, no. Okay. Hi, Marella.
Hi.
All right, now I can hear you guys. I don't know what was going on before, but now I can't see you, but I can see your names on the board, so that's fine. All right, so we just did the 3rd page. I'm going to read across so you have the numbers, okay? So top, the height is 25 meters, that box that's already filled in for you. We're at 24,500 joules of potential energy. 0 joules.
Wait,
to the box in on the 3rd page, the table, where it says location, height, potential, kinetic, and total.
Yeah.
Okay, so I'm just going to read you the numbers across. All right, you ready?
Mm-hmm.
So for potential energy, it's 24,500 joules. 500 J. Kinetic energy is 0. Total energy is 24,500 joule J. All right, middle. The closest I could get to the middle was 16.8 meters. So it's still a little high. Potential energy at that it's on the board right now, so 16,491 joules. And the kinetic energy is 8,009 joules. And if you add it up, the total energy is 24,500 joules. All right, so I'm going to hit play. And I'm going to pause it at the bottom. And we see that potential energy is now at 0. Kinetic is 24,500. And total would be 24,500. So how do the potential and kinetic energy change as the sled moves down? So what happens with potential and kinetic energy?
They switch.
They switch. Perfect. You can use that word. Okay, so B, add the potential and kinetic energy for each location. We already did that. Find the total energy. What did you notice about the total energy? So looking down to total energy, what happens?
It stayed the same.
Good, it stays the same. Okay, so according to the law of conservation of energy, energy can be changed from one form to another, but it cannot be created or destroyed. So that means the total amount of energy at the beginning is the same as the total at the end. All right, number 2, explore. All right, so we want to just kind of play with the height of the sled and the mass of the sled to observe the effects and the change of potential energy. So how does potential energy change when height is increased? So I'm going to reset it. So right now at 25 meters, we're at 24,500 joules. If I bring them up, we can see that it increases as height increases. So it went up to 49,000. So for A, it just increases. How does potential energy change when mass increases? So we're going to leave them there so we see what the potential energy is, and we're going to increase the mass. And we can see that it went up significantly. So it went up 9 to 98,000. So it increases. All right, compare a sled's potential energy at 10 meters to its potential energy at 20 meters. So I'm going to bring them down to 10. And we see that it's at 19,600. I'm just going to make a mark or write it down on my paper. And bringing it up to 20. It went to 39,200. And I'm assuming if we multiply that, then all right, so if you multiply the 19,600 by 2, so we're doubling the height, then it increases by 2. The amount of energy increases by 2. It doubles. Does that make sense? So if you double the height, the potential energy doubles. So how does doubling the height affect potential energy? It doubles potential energy. All right, so compare the potential energy of 100 kilogram sled at the same height, to a 200 kilogram sled. All right, so if I leave them at 20 meters and it goes to 19,600, and then we go back to the 200. So same thing happens. Doubling the mass will double the potential energy. All right, are we all good with that? Anybody need me to repeat any part?
No.
Okay, so continuing to the next page, measure, click reset. Oops. All right, so we want to set the red sled mass to 100 kilograms. And put one snowman there. Drive the sled to the top of the hill. And then play, pause the snowman right before he hits, or pause the sled right before he hits the snowman. All right, so what's the speed of the sled before he hits the snowman? We're at 31.3 meters per second. Kinetic energy, looking up, is 49,000 joules. And then we're going to watch him hit the snowman and record the speed and the kinetic energy. So I'm going to play. And we can see the speed has decreased to 24.08 meters per second. And the kinetic energy has decreased to 29,000 joules. So how much energy was destroyed? Reed, come. All right, who has an answer? How much energy was destroyed? You can do that math. Hi, Jamie. We're on the 4th page now. Activity B. What's 49,000 minus 29,000?
20,000.
How much?
Yeah, I got 20,000.
Okay, good. All right, so now we're going to click reset. Drag the sled to 40 meters. And set its mass to 160. We went decreased by 10 meters, but increased by 60 kilograms. All right, so what's the potential energy? We're at 60,720 joules. And how many snowmen do you think he can destroy? He destroyed one pretty easily at before. Give me a guess, and we'll add the snowmen there.
3.
3. Okay, so I'll add. Well, let's write down 3 for B. And we'll say the mass increase. Let's see, the potential energy increase. For the explain your answer, we'll just say potential energy increase. It actually wants us to set it at 5 to see how many snowmen he'll destroy. So hit play. Ooh, good guess. All right, you destroyed 3. Hi, Youssef. We're on page 4 in the middle of the page. Starting at extension 1, right in the middle, number 5. All right, so the formula. So this is the equation parts that I wanted you guys to practice for the test that's coming up next week. So the equations are going to be given to you, so it should be pretty easy, hopefully. You just need to understand how to plug everything in. So in this formula, PE stands for potential energy in joules, M stands for mass in kilograms, and H stands for height in meters. G is the acceleration caused by gravity, which we've talked a lot about already. So it's 9.8 meters per second squared. This means that every second, the speed of a falling object increases by 9.8 meters per second. So calculate the potential energy of a sled. And I don't think we have a calculation on there, so we're going to have to do the math. So we have 20 kilogram sled at 40 meters. So show your work. So our M is the mass, which is 20 kilograms. And we're going to times that by gravity, which is 9.8 meters per second squared. And we're going to times that by the height, and it's at 40 meters. All right, so for this question, we're just multiplying all 3 numbers together. Anybody have a calculator available?
Yeah, I have one.
Let's see what you got. 100. Sawyer got 100. Let's see if it's right.
I got 7,840.
Very good. Okay, so 7,840 and it's in potential energy, which would mean it measures in joules. So when you do the K times
600.
it's not 600, honey. Kg times meters per second squared times meters is how we measure joules. So 7,840 joules is our potential energy. All right, so now, does anybody have questions on how to calculate potential energy? I know that was only one practice problem, but if we had that, if we had a question like that, would you guys be able to figure out how to do it?
Yeah.
Okay. All right, so moving on to kinetic energy. Again, kinetic energy is in joules. M stands for mass. V squared stands for the speed squared, or speed times itself. So we want to know if we have 1/2 or 0.5 times the mass, which is 20 grams, times the velocity is 28 meters per second. And then we're going to square that 28. All right, so I'm going to do the square first. So 28 squared. So 28 times 28 is 784. Did you guys get that too?
Yeah.
Okay, so that's our speed squared. Then we're going to multiply that by 20 kilograms and then times 0.5. And you're going to unplug my computer stuff. 20 times 0.5. All right, so I'm getting set the same number. Do you guys get the same number?
Yeah.
All right, perfect. Stop it. All right, so turn the page onto activity C. All right, so this time we're gonna do 2 sleds. So I need to click up at the top for 2 sleds. Show the energy. Energy is on. The red sled mass to 150. And it's height at meters. The blue sled mass is at 100, and its height is at 35 meters.
600.
No.
100.
Okay, so the potential energy of the red sled up at the top, it tells us it is 29,400 joules. The blue sled is 34,300 joules. So which sled do you guys think will push the other sled back when they collide?
The blue sled will push the red sled.
All right, good. So let's play blue. And because it has more what?
Potential energy.
Good. It has more energy, more potential energy. So let's watch. Oh, wait a minute. Did I write that down wrong? Okay, I'm not sure.
Okay, the red one's stronger.
The red one's stronger?
Yeah. So the blue one is not gonna win. One of these said the blue one's gonna win.
But wait. So he has more potential energy, but I guess his momentum is stronger. I'm going to calculate their momentum. Who remembers the momentum equation? Anyone? Sawyer, what did you just do? You guys also there?
Yeah. I'm trying to think.
All right, so it's the speed, the velocity, times the mass. All right, so the momentum of the red sled is 2,970, and the momentum of the blue sled is 2,619. So even though he had more potential energy, the red sled ended up having more momentum, which is why when they collide, they go in the direction of the red sled. So this is kind of like the crash scene investigation that we did yesterday.
Okay, I went for a stronger.
Yep. Okay, so we tested it. They stuck together. We hit play. Let's pause after the two sleds collide. Which sled won the war? So now we're going with red. And did it surprise you? Yes, right? After the collision, what was the kinetic energy of each sled? All right, so the kinetic energy of the red sled is 148
I said 100.
joules. And the blue sled is 98 joules. What happens to the combined energy of the sleds when they combine? The combined energy of the two sleds when they combine. All right, so looking at this, they obviously significantly decreased when they combined. They canceled each other out. Okay, so the answer to B is that it decreased. Because energy is conserved, or the lost energy has actually been changed into other forms. So looking at the two sleds, okay, you gotta go away. What affected some of the energy caused? Okay, so if we look at what the sleds look like, we can see that they crashed into each other. So the energy was transformed from the moving energy, and when they crashed, it go away. It changed the sled. So the sleds themselves changed. So we're gonna write the sled crumpled. All right, so here we come down to the momentum for so we're gonna calculate reset. We're gonna calculate the momentum now, which is what we had done before. We got why red sled was stronger than the blue sled. So remember, P stands for momentum, M is the mass, and V is velocity. All right, so we're gonna hit play and then pause right before they collide. All right, so the speed of the red sled was 19.8 meters per second. Momentum of the red sled, we already calculated that, so it was 2,970. Speed of the blue sled was 26.19 meters per second, and the momentum was 2,619. Anybody need me to repeat those numbers?
What was the momentum of the blue sled?
Blue was 2,619. 2619.
And what about the red one? I didn't get that one down.
2970.
Okay.
All right.
What was the speed of the blue sled?
I'm sorry, the speed of the blue sled. So it's right here at the bottom, 26.19 meters per second.
Yeah.
All right, last page. So we are at gather data. We're gonna reset one more time. For each combination of sled masses and start height below to play. Okay, so we're gonna do red sled at 50 meters. The red sled mass is 20 kilograms. So we want to play it to see what the speed momentum is. So oh, I didn't change the blue. Sorry, I'm going to reset it again. So blue should be at 100, but down at 10. All right, so right before I don't know if that was right before, if that counted, it's crashing. I'm going to play it one more time. All right, so they didn't crash. All right, the red sled speed right now is 31.30 meters per second. So we're doing the whole column under 1. So if you go down to blue sled speed, we're at 14 meters per second. The red momentum, so we're going to take the speed, which is 31.3, and times it by the mass, which is 20, and we get a momentum of 626 for the red sled. The blue sled momentum is its speed, which is 14, times its mass, which is 100, and that equals 1,400. So when they collide, if I hit play, which sled should win? Red or blue?
Blue.
Blue. Good. All right, so now we're going to do the same thing. So reset. The red sled goes to 25 meters. The blue sled goes to 20 meters. Red sled mass is 120. Blue sled mass is 130. All right, so I'm going to hit play. That again. All right. All right, so we have a speed for the red sled, 22.114, not 114, 14 meters per second. Speed of the blue sled is 19.8 meters per second. The momentum, anyone want to try to calculate this on their own to know that you know how to do it? Because this is part of your test. Any volunteers?
2,656.8.
Very good. So it's 2. So red sled is 2,656.8. And the blue sled is 2,500. Blue sled is 2,574. So which sled should win? Red.
Wait, what? My thing disconnected.
Okay, so we just did the what did I just let you back in, so I don't know where you left off. What are you missing? Column. Blue, the momentum or the speed?
All of them.
Okay, so number 2, you're going down the column, right? Did you get all the first
one? That's when it
I'll just take a picture of the table. And
okay.
Okay.
All right.
All right, so when they crash, the red sled wins, not by very much, but by a little bit. All right, last one. We're gonna bring him down to 5 meters and 100 grams. He's gonna go up to 45 and 40 grams. And we're gonna see their speed. All right, so we have red sled speed is 9.90 meters per second. Blue speed is 29.7 meters per second. All right, so to calculate the momentum, all right, so 9.9 times 100 is 9 690 for the red sled momentum. And 29.7 times 40 is 1,188. So who should win?
Blue.
Blue. Blue won. All right, so in each trial, circle the greater momentum value. What's true about momentum of the winning sled in each contest. So momentum determines the sled that's going to win. Or we'll do the greater momentum, then the sled will win. So greater momentum equals the winning sled. If you knew each sled's mass and speed, how could you determine which sled would be pushed backward in collision? We already figured that out because we calculate the momentum. All right, so B is you just calculate the momentum. You have to go away. All right, click reset, select sled bounce. So do I do that? Oh, okay. All right, so down here, we're not gonna have them stick together. They're gonna bounce off of each other. In this collision, large springs cause sleds to bounce off each other. Using the same setting from the last trial, click play. All right, what do you guys notice about their height when they go backwards?
The blue one goes a lot higher.
He does go up higher. I'm gonna reset it. Notice the height that he's starting at. So the red is at 5 and the blue is at 45. So when we hit play and they collide,
They almost go to the same. Well, the red height increases and the blue one decreases.
right? So they're going back a good amount. But some of the blue force is added to the red. Some of the red is the red takes away from the blue. So, but they're going back to similar height. Whatever you guys put there is fine. All right, extension. Click reset. Without changing any sled's masses or heights, record the potential and kinetic energy of each sled and find the total energy. All right, so before collision, we have the red potential energy. Oh wait, so I need to hit play and then we're gonna right before they hit. All right, so right before they hit, the red potential energy before collision is
What?
0. The red kinetic energy is 4,900 joules. Blue potential energy is 0. Blue kinetic energy is 17,650 joules. The total energy of both. All right, so we're just adding up the energy. So 49,000 plus 17,640. So the total energy for the before collision is 22,540. Anybody need me to repeat any of those? Okay, so I'm gonna play.
Total energy.
Which one?
What was the total energy?
22,540. Okay, after collision, the red potential energy right now is at 93 joules. The red kinetic energy is 8,007 joules. Blue potential is 5,085 joules. Red potential is 9,355 joules. So we just have to add all those numbers together. 93 plus 8,007 plus 5,085 plus 9,355 equals. And we are at 22,540. So is energy conserved in this type of collision? Yes or no?
No.
Is the total energy before collision and after collision the same?
Yeah.
Yeah. So the answer would be yes. So, and we'll just say the total energy before and after are the same. All right. Josh, you're joining us a little bit late. We actually just finished the whole packet. Hopefully I recorded this and I'll be able to post it online, okay? Do you have any questions before? Does anybody have any questions before we go?
I just don't have the chart, but you're gonna send that to me, right? Or post the video?
Morella talking, right?
Yeah.
Yeah. I'll send, it's just the last page. You want me to send it to you?
Yeah.
Are you on my reminds?
Yeah.
Okay, so I'll be able to send it to you that way.
Okay. Then I'll just do the first page of my own.
Okay. Yeah, the first page we did the first stuff anyway. But if you were, I could send you that one if you want.
Sure, activity day, yeah.
Okay. Anybody else have any questions? Josh, I'll stay on with you for a minute if you want. All right, so the rest of you guys, you're good. Should have all the answers, and as long as I recorded this, I will post it. It'll be in 2 parts because we did the first part and it wasn't working. Hopefully that works, at least to see my part of it, and then we logged on again, and I'll post the second part, okay?
Right.
All right, guys, I'll talk to you later. James.
Bye.
Bye. Josh, you want me to show you how to start it? Josh? Josh, can you hear me? Josh? Josh, can you hear me? All right, Josh, since you can't hear me, I don't know what you're going to need help.
Praise to the Lord.
All right, so I'm going to log off right now because I don't think you can hear what I'm saying.
Get together and feel all right. Hear the children cry.
Aiden, you just missed out. We just finished it.
Oh.
I'm gonna, hopefully I recorded it. I was having some problems earlier, so it's gonna come in 2 parts. So as long as I recorded the second part, I will put it back on. But before I close out, do you want me to go over any part of this really quick to show you how to do it in case I didn't record it?
No, it's fine.
You sure?
I thought it was at 10 because that's when you did the other ones.
I know, they gave us a schedule now. So Mr. Amato gave us a schedule. So we need to be coming on it. Science is supposed to be 9:30, but Mr. Siciliano said that I could take his time. So I started at 9, but the 9 o'clock one wasn't working. So
doing something weird, Mom.
I might just start doing them at 9:30 because I think 9 o'clock is a little too early for you guys. You're not waking up in time.
Like 9:30 at night?
No, in the morning still. All right.
You think 10:30 is too early?
No, I don't think 10:30 is too early, but 10:30 overlaps with other teachers' Zoom times.
Oh.
So they assigned the times. I could do 9:30 is what they gave me, but Mr. Siciliano said he won't be doing this, so he said I could take his time. So that's why I started at 9 today.
Oh.
All right, but I'll probably do another one explaining all the math. If anybody has any questions, more of like an open question thing, maybe I'll do it tomorrow and Monday before I give the test out. Okay? All right, so check in on Google Classroom for the time. I'll post the times I'm going to do it, okay?
Bye-bye.
All right, have a good day.
I like that sled racing, and they go like. Boom,
Yeah, that was fun for you.
Yeah. Hey, why are you doing reflex?
I don't think I was on Reflex.
The loop
Okay, watch out.
Don't put my belt on. Belt on. Belly button on. Belly button on. Mama,
Here we
can
go.
you put my belly button on?